As we learned previously, virtually everything we use has to be manufactured in some way. It's impossible for nature to produce a functional airplane without a bit of human intervention. Raw materials are turned into semi-finished parts, which are then used to create the final part according to a design. Though most of my day is spent in the lab, answering all kinds of scientific questions, sometimes I like to express my creative side with a bit of origami. We could think of origami in terms of the manufacturing process. At the factory, wood pulp, the raw material, is processed into thin sheets of paper, the semi-finished parts. Our final part is created by folding it according to a specific design. In engineering, a sheet of metal isn't unlike the sheet of origami paper. And in fact, metal sheets are a very common semi-finished part in aerospace engineering, since they can be formed relatively easily. But what happens when we try to form a less ductile material in the same way? Let's head over to the hypothesis board to organize our thoughts and come up with our hypothesis. We already know that ductile materials can be easily bent into shape. Brittle materials, on the other hand, tend to fracture quickly and without warning. So I will make the following hypothesis. Unlike a ductile material, a brittle material cannot be formed into a new shape after it has been created. Now that we have our hypothesis, let's define our experiment. Our experimental design is pretty straightforward this time. We'll need 2 sheets of material, one brittle and one ductile. Metal is the natural choice for the ductile material, and let's use a thermoset composite sheet for our brittle sample. You can probably already tell that this experiment will be a bit different from our previous ones. Here, since we're using engineering materials, we don't expect you to have these on hand at home. We'll use them for now to perform our experiment, but we'll have a do-it-yourself suggestion later. To deform the materials, it's probably easiest to try and bend them out of shape. I could try to bend them myself, and I'm pretty strong, but I don't think I could get very far trying to deform our sheets. Instead, we'll use a special machine called a brake to help us out. The brake works by clamping down on the sheet, while a larger plate hinges upwards to bend the sheet up to 90 degrees, thus deforming the material. So now that we have our experimental design, let's head over to the Delft Aerospace Structures and Materials lab to see this experiment in action. Safety glasses on! Here you can see the metal sheet being placed into the brake. It gets clamped in place to prevent it from shifting, and a lever is pulled to allow the hinged plate to bend the sheet upwards to 90 degrees. When we take it out, we can see that the metal sheet retains its shape. It moves back a little bit after the load is taken off. This is called springback. But it certainly doesn't go back to being a flat sheet. Now let's try the composite material. The same procedure of clamping and bending takes place, but whoops, the result is a little bit different. Instead of creating a smooth angle, like in the metal, the composite sheet fractured and splintered. There is a clear hinge at the brake line, and the sides are no longer connected. If you look even more closely, you might be able to see some of the fiber layers in the crack. Well, one thing's for certain, that composite is definitely not usable anymore in an aerospace structure. So what have we learned from our experiment? Well, we hypothesized that a brittle material can't be formed into a final shape once it's been created. In the experiment, we saw that, indeed, the composite material broke when we tried to bend it. Thus, our hypothesis has been confirmed. But what does this mean for composite manufacturing? If we can't form them afterwards like metals, then how can engineers create different shapes using these materials? Well, prior to curing a thermoset composite, the material is flexible and shapeable. This is where engineers plan to give a composite its final shape, by using a mold, for example. Since the material cannot be reshaped after curing, it's important to make sure that the composite will cure in its final shape. This contrasts with metals, which can be cut, formed, and reshaped in numerous ways at nearly any stage of the manufacturing process. Maybe one day you'll design composite parts and have to consider these manufacturing differences. Oh, I almost forgot. Even though we used carbon fiber composites and special equipment to do our experiment, there is a do-it-yourself way too. In the text below this video, you can find instructions on how to make paper mache, which is, coincidentally, also a composite material. You can whip some up yourself, maybe look up an origami airplane pattern, fold the design with both regular paper and paper mache, and try to observe the differences between the two materials.